All right, and hello everybody, and welcome to the number one generative AI meetup podcast in the world. So today we have a very special interview and guests. So today we are doing an event in Palo Alto at SambaNova's headquarters. So for those that don't know, SambaNova is a chip startup that is competing with the best of them. So they are competing with Nvidia, Cerebras, Grok, and I think that they are going to be competitive. So it's very exciting because together with the South Bay Gen AI meetup, we are doing one of their first events. So if you're here in person, thanks for coming. If you're just listening to the podcast, thank you for listening. So today we have two special guests. We have Urmish, who is the Director of Machine Learning here at SambaNova. And we also have Raghu, who is part of the founding team at SambaNova and actually turned his PhD into the hardware that this company is now using today. So thanks so much for taking time out of your busy day and sitting down to chat with us. So can we kind of maybe start and would you be able to maybe give like a brief rundown of what is SambaNova? Like, how are you different from the other competitors that you have?
Yeah, so maybe I can give a high-level picture and then we'll maybe dive deeper as a conversation might take us. So SambaNova, he already alluded to this in your introduction. We are effectively a full-stack AI company at this point. So we make our own processors and we have our own different kind of architecture called the reconfigurable data flow unit, or the RDU. We've taped out a few generations of it, and the most recent generation is called the SN40L. So SN SambaNova 40 is the fourth generation, and L is, I don't quite remember what L is. And that's the most recent version that we have taped out, and it's in production right now. People are using it. We are a platform where we do both training and inference. And recently, of course, for the past few months, we've had a cloud inference API offering. So, the core, I would say the core thesis where we are different from architectures like Nvidia. You can see that my background is computer architecture, so I'll answer your question with that lens in mind. The architecture does not have the traditional notion of instructions that you stream through. It works in a different way. So because of that, it's a data flow architecture. So because of that, we have to build our own compiler, which is the other half of, arguably the more dominant half of SambaNova's advantage, I would say. As of now, we've been mostly focusing on inference through the cloud sort of API offering. At least that's where all the limelight is being shown. But we've always been a training and inference player in the market.
Okay, very cool. So you mentioned that you have the RDU, which is, I guess, it's just the reconfigurable data flow unit. Could you maybe go into a little bit more detail what that is?
Yeah, sure. So as the name stands, it's called reconfigurable data flow unit, and the genesis of this architecture comes from some research done at Stanford that I was lucky to be part of. The core idea behind data flow architectures in general and reconfigurable RDUs in particular is that typically when you execute something on any architecture, you specify what to execute in terms of a stream of instructions. Like the von Neumann style architecture, you stream through a bunch of instructions, and as the instructions flow through your processor, they have side effects where they load, manipulate results, store it back, the results to the memory. RDUs and the data flow architecture concept in general, it doesn't have the traditional notion of instructions. So instead, the RDU has like a sea of, like a two-dimensional grid of compute and memory units. They are kind of all talking to each other in this interconnect fabric. And when you program the chip, instead of specifying the sequence of instructions, you actually statically assign a role to each of these units such that the whole unit behaves like a a compute graph. So at this point, there's no stream of instructions flowing through your chip. It's mostly every unit is going to do one or a few things that are pre-programmed, and you flow the data through it. So every unit is going to fire and do its thing when its data is available and push the results out to its next set of units. The main advantage with this is you don't have to pay the overheads of these instructions. Building an instruction fetch, decode, register file, branch break, all of these things consume some overheads on your silicon. And it also introduces a bunch of these synchronization overheads. So you lose performance because of that. The primary thing with AI inference, at least now, is performance. Like, you need to run as fast as possible, remove bottlenecks. And with the data flow architecture, data just naturally flows. So there's no waiting, no forced synchronization points, things like that.
Yeah, and as a model builder, it's just very cool to see. You write your code in PyTorch, and then you see this thing running really, really fast. Like when you're running things on GPU, say you have a neural network graph, right? Each operator is a node. You can see each operator running step by step, right? When you're running things on RDU, the compiler that we have, the hardware that we have, it enables to sort of spatially lay out the entire graph, and then you can see all of those things running simultaneously, and that's where you get the performance. So it's pretty cool to see just the same PyTorch code running on GPU, how it runs, the bottlenecks and slowness that you see, and then switching to RDU, the same PyTorch code, you see the 6x to 7x performance benefit that you see on our stack right now.
Okay, interesting. So you can just easily switch between like the GPU and RDU. Yeah. It's like a one-line change.
Yeah. Very, very driven amount of change.
Okay.
So it seems like that's where your competitive advantage is, mostly for inference. And you mentioned like 6x performance boost versus traditional GPUs. Anecdotally, I've seen like some 10x faster performance.
Yeah. So not just inference training both, right? It's just right now, market wants us to talk about inference the way I see to talk about inference. If you look at what we have talked about and the papers that we published for the last 3 years, we have talked about faster training performance. In last year, we did work together where we showed for these large language models, you can do 6x faster training than GPUs using some algorithmic innovations and converge to the same accuracy. In fact, we trained a 13 billion or 70 billion parameter model till
30.
Yeah, to a sort of for almost 500, 600 billion tokens at 6x sort of speed and got to the same accuracy that the model should be on a GPU. So training inference both, right? We go beyond training and inference to sort of other domains also, but right now inference is what we sort of talk about given where the market is.
I think that's fair to talk about inference, but I think that it would be interesting to know kind of like what else these chips could do. Because when I was looking at your website, I kind of got the impression that these chips could only do kind of training inference. But as we were sort of talking about earlier, you mentioned it was kind of like a general purpose type chip. What other types of use cases do people use this chip, or like could they use this chip for?
Yeah. So we have quite a few customers who are national labs who use our chips for scientific computations, for example. So we've certainly made certain design choices that suits the chip better for AI. Like for example, if we just look at the chip speeds and feeds of the SN40L, it's about 630 odd teraflops of bfloat 16. So the difference really between AI and maybe other domains is that some domains are okay with data types like bfloat 16, but if you're doing scientific compute, you might require FP32, like the full single precision data types. So our chip is capable of doing both. It's bfloat 16 as well as floating point. The capabilities are different, as it is the case in, say, Nvidia, for example. But at the end of the day, the architecture of the chip and its capabilities, they are able to run pipelines of parallel operators in a data flow fashion. And that's the way I put it. So I want to introduce one term here and I'll describe what it is. So the architecture has been inspired by some prior research on what we call parallel patterns. And really what parallel patterns is it's just a higher order programming construct which represents how a particular operation is getting parallelized. So an example would be, and if you imagine like a mathematical operator like dot product, where you take two sort of one-dimensional arrays and you multiply and add them together, you get one value out of it. You can decompose that into a map operation or a zip which means it's an element-wise multiply of the two things, and then a reduction. So zip and reduce would be the two operations. There are other operations like this, map, filter, group by, sort, things like that. And very early on, we know that these primitives, whether it's AI or scientific computing or other domains which can be accelerated, you can break down the thing that takes a lot of time into these components, into max, zip, reduces, etc. So we have a path to taking a compute graph expressed like that down and program it on the RDU. So in that sense, any dense, sparse linear algebra kernels that forms the heart of pretty much any compute workload, you can actually program and accelerate it on the RDU. Now, from a business point of view, we of course know that inference is, AI in general and inference in particular is one of the hottest burgeoning markets right now. So most of the messaging on the website is probably on that. But the underlying technology is not built to saying, it's only inference. We would have made maybe different design choices if it was only inference.
Yeah, I think that makes sense given how much of the startups are using pre-built models and just running with it versus like the handful of companies that are actually training these larger models. But for the training case, Nvidia seems to have like a moat with the developer ecosystem they've built with CUDA. And you mentioned like it's relatively easy to port over the inference side. How hard would it be for some company to like port over their whole pipeline into?
It's not that difficult, right? So I think we need to understand that when people or ML developers operate, they operate at a PyTorch level. So CUDA doesn't matter. CUDA is in the backend, right? You sort of traverse your graph and then figure out what, depending on your hardware, that op is scheduled, right? So if your hardware is at sort of Nvidia, you use the CUDA kernels. At least that's personally how I see it. And if your hardware is our hardware, so it will be sort of mapped differently. So from an ML developer point of view, again, it doesn't really matter, right? For a trivial amount of change, you can sort of port from PyTorch, take a PyTorch code on GPU and sort of run it on our hardware. And we see that like we have a lot of training customers, right? A lot of them in the national labs, a lot of them in the enterprise cases. And we see them successfully training a lot of different large language models in a wide variety of languages. So at least the way I see it, it's not a big deal.
What about in terms of integrating with these cloud service providers? So let's say a developer can do both training inference easily. Another moat that NVIDIA has built up is like all the deep integrations they have with all these cloud service providers. Because apart from just the fast chip, there's a lot of overhead that goes into building large servers. There's like networking, switches, memory, and things like that. How do your systems, like you mentioned you provided training as a service, inference as a service on your own hosted solutions. Can people use now or in the future SambaNova Systems through AWS or Google Cloud or Azure?
Yes, I think so. Firstly, the way we sort of structured our business model, right? We sort of, when he said you're full stack, we are really full stack. We actually ship to a lot of our enterprise customers. We ship our hardware to them and manage it for them, right? So we manage effectively the way I see personally as a developer. And maybe there is some nuances here which I'm missing, but as a developer, the way I see it is the entire data center is managed for you. So all of the things that you talked about, networking, etc., is taken care of, right? You get APIs for fine-tuning, training. You get APIs for fine-tuning, pre-training, inference, whatever you want to do. How the things get mapped to the entire distributed cluster, etc., is all hidden from you, right? So in a way, we are already doing that. We are kind of doing it on-premise behind sort of a customer firewall. Integrations with cloud providers, etc. I personally don't see a reason why sort of that won't happen. Why we are not there, etc., is something that I'm not aware of.
Yeah, I think there's no technical reason, as in because if the programming interface is something that's standardized, and it's optimizing anything is the usual mantra is like write once, optimize everywhere kind of a thing. So there's always, when you want to extract peak performance, there'll be something you'll have to do on every platform. So I don't think we're immune to that. But that said, we still enter from the same tensor torch abstraction. So there's no fundamental reason why that wouldn't happen. So it might happen in the future. We just haven't done it yet.
I mean, we are a startup. As a startup, one of the important things that you learn is pick and choose your battles, right? You need to build that ecosystem out as you build the company out. So And picking and choosing a battle means you try to understand where you can get the most business as of today and try building things up there.
Looking at...
There's one tangential point on this before we move on to the next one, which is, in addition to what Urmish just said, I think Urmish kind of alluded to this earlier, so I just want to highlight the point again. One is the integration maybe with other cloud providers, and there's something there. But the other important thing is some of our customers, something we've learned as well, they don't, for a variety of reasons, their data, they want to maintain control over it.
Yeah.
They want it to be within their firewall. They're not okay uploading it to like a cloud service for regulation, security, sovereignty, whatnot. So for a variety of reasons, there is a concrete use case for people holding these machines behind their firewall. They want to fine-tune, train, deploy stuff to their employees based on their data, and there's a big use case, big clientele in that space. And SambaNova is effectively one of the bigger players in that space, where it is you get your APIs for training and inference, and you get it on machines which are behind your firewall. So in a way, not being on GCP and not having to access via some other third-party provider like that is a benefit for those clients.
Yeah, 100%. I mean, it makes sense. I mean, I think a lot of companies, they are sometimes having like very confidential and proprietary data, and they don't necessarily trust the big clouds, and they just feel more comfortable having their own hardware. So I think that is very true. That it's a really valid and like good market segment.
And it's a universal problem. We have customer deployments both across national labs and enterprises, spanning so many countries and continents. So it's not just one specific region or a specific set of countries. It's everywhere this is the same problem. They want their hardware behind their firewall so that the data is protected with leaks.
For sure. So one thing I was curious about is it seems like there aren't many huge limits to the hardware from if I understand or what you were saying. But we were curious. So right now on your cloud offering, I think the biggest model you have is the Llama 405 B model, which is running well. I tried it out. It was very fast. I was quite impressed. Amazing, I would say. But I'm curious, what's the limit? So some people say there's rumors that OpenAI has a 1 trillion parameter model. I don't know if they do, but what if we want to build GPT-5, GPT-6, and we want something bigger? We don't want 1 trillion parameters, but we want 10 trillion. Is that something that is possible to run on the hardware right now?
Yeah, so I'll answer your question maybe by dissecting it into maybe two axes. One of them is, how are you going to run different kinds of model architectures? And then what's the limit in terms of the size? How big, and then where will we sort of fall apart, for example? I think model architectures, maybe the prior discussion probably covers it, which is if the entry point is similar, then you can express whatever kind of model architecture through a PyTorch through the PyTorch layer. So in that sense, we've already we've run a mixture of experts, transformers, convolution models, and so on. So the breadth is not a problem. That's the generality of it. Now comes the size. Saying, okay, how big can you go? I think this is where if we sort of divide up the AI market segment into, the accelerator segment into maybe 3 categories. One is the GPUs and GPU-like architectures. The other one is maybe SRAM-only architectures. It's the memory system choice used, and maybe US. I'm singling out US because I want to kind of compare against these 2 buckets. If we look at GPU-only architectures, the bigger the model, the more memory you need. That's just the universal truth. You need to store them somewhere. You need to stream it from somewhere and do all this. GPUs only have HBM attached to them, high bandwidth memory. And the typical trade-off with HBM is you get more bandwidth, but you get lesser capacity. So most GPUs have 80 to maybe 100, 150 gigabytes of HBM. That's usually the ballpark. So models which are bigger, like a 1 trillion parameter model, you shard it because you want to spread out the memory required over multiple GPUs for the capacity reason. SRAM only architectures, maybe Cerebras, Grok, maybe there are others, but those kinds of architectures, it's the same idea, but you spread it out over SRAM, on-chip or on-wafer SRAM. But that's where you hold it. Now, SambaNova with SN40L specifically, we have two types of memory. We also have SRAM, we have HBM, but we also have DDR, which is high capacity but low bandwidth directly attached to the socket. So what that enables us to do is we can play memory optimization, we can adopt memory optimization algorithms where you can use DDR to store capacity. Like you can host not just one, but several models. You can keep them in DDR. Use the most critical things, use HBM for that, which is high bandwidth. And then on-chip SRAM gives you the data flow and the operator fusion capabilities. So in that sense, the limit is really as big as our DDR, which is like 24 terabytes, 12 terabytes, I should say, per node, which is 8 RDUs. And if we want to go larger, we have the software mechanisms to shard it across multiple sockets. So in that sense, I would say the larger the model, the better suited we are to kind of take advantage of that.
Yeah, the way I personally think about it is for the same footprint, we can run the largest models amongst all of the companies that you mentioned, right? You think about it, HBM, SRAM even smaller than HBM. So if you want to run a larger model, you have to scale out so much just to run a single model, right? I think we heard these numbers even for Inference. One of these companies had to run at 576 sockets for, I think, a 70B model.
70, yeah.
We run 70B model on 8 sockets. We don't need 576 sockets, right? Just because of this hierarchical memory that is created. And similar on GPUs, a lot of issues with scaling. So, and then we see that, right? We see this sort of being very useful. So to coming back, you can run as big a model as you want. The bigger the model, then you sort of run into these memory constraints. The more memory that you hold, the bigger the model you can run on a single socket. And if it sort of run out of space on a single socket, you scale out, right? And for us, the advantage that I personally see as a developer is that I have an option to scale out or not to scale out. It depends on how much capacity that I have, right? Because we have this larger memory attached to the HBM and the SRAM. While for the other providers, the only way is to scale out. And we saw that being very useful, and our customers see that being very useful. Like we have trained 13B, 70B, 176B parameter models. We've gone even larger in training. And depending on how big a cluster and how many nodes are available internally in my sort of ML farm, the data center that I have, I can sort of change the size of the socket count that I want to train on. You can't really do that on a GPU or other architectures because to fit that model out, you need X number of sockets, right? So if for whatever reasons you don't have those X number of sockets to start with, it becomes very hard for you to train. So the size of the model is not a problem. In fact, I think for inference, we can run 5 trillion sockets on a single node, 5 trillion sort of parameters on a single node. Is that true?
Yeah, I think it's more than that probably. Whether, 5 for sure. Yeah.
But of course, you can scale out any way you want, right? The system we have has this capability of doing whatever you want. And that flexibility makes it really useful for most developers in different deployment scenarios.
One thing I found funny was you mentioned you use the DDR RAM, the slow, high latency RAM, almost as like a storage solution, where on personal computers, that is like the fastest memory that we have.
Yeah.
Like a laptop.
Yeah. It shows the appetite of models today. Yeah.
So I guess on those lines, what is the smallest model that it would make sense to host on your servers versus just running it locally? Is there like trade-off where your chips are going unutilized if you run like a really small model?
How local are we talking about here? Is your phone or your
maybe
laptop?
like a phone, laptop, something like that.
The thing is, as you go smaller, you can store more and more things on your SRAM and make it run really, really, really fast, right? Insane speeds. The way I think about running locally versus running on cloud is just a choice, depending on privacy concerns, latency concerns, and things like that. But for us, I never think of a smallest model where things don't make sense. Like the smaller the model, the better it is because you can run extremely fast.
Right. And also, I think there are two. If you think about what all takes up memories, One of them is model size is one, which is small versus large. The other one is how big of a context is that model. If it's a small model, but you're looking at 1 million tokens, you will still require a lot of memory. And you'll still require the same bandwidth. So there you're back to saying, okay, my model is fast, but I still need, I need to keep my context somewhere. And then it's the input. If it's a multimodal thing, it's like an input size as well. So all of these things require capacity as well as bandwidth. So I would say for a very, very small model, which operates on also a small to moderate input sequence. When I say small, I mean something that fits in your CPU cache, for example, like hundreds of megabytes. Well, even less than that. Maybe you can run it on your laptop. But when you're using that in conjunction with speeding up a larger model, like speculative decoding, for example, or you're building some agentic system where you want a small and large model to sort of ping pong between each other, you'll quickly run into this problem. Okay, small model runs here, big model runs there. Someone has to manage the memories and so on. So I would say anything where you're off the CPU's memory, which is maybe like 50, 60 megabytes of memory that you have on chip generally, you'll start seeing the impact of, okay, I'd rather use something like SambaNova to run it.
Talking about agents, it seems like that's the new wave of hype nowadays, because these models are getting somewhat plateaued in terms of their performance across all of these competitors. And the only way to push more performance is by building some kind of agentic behavior, just like throwing more compute at the problem and having these models just think through their steps and work with each other. So if we were to build an agent with like a SambaNova architecture, would it be better in terms of performance if we were to host like multiple models in like the same environment and have them like locally talk to each other?
Oh yeah, definitely. I think our platform is really well suited for the agentic paradigm, right? So there are a few things that you require for agentic paradigm. One is extremely fast inference, because each model needs to run at a very fast pace. Either you're generating multiple answers and selecting one of them, or you're generating a sequence of multiple answers while each answer is getting corrected with some feedback. So that's fast inference that you need. The second thing sometimes a lot of these agentic systems need is multiple models collaborating with each other, right? You talked about kind of this three-tiered memory architecture, SRAM, HBM, DRAM, right? That allows us to host all of these different multiple models simultaneously and instantly swap between them. On a different architecture like GPUs or the other SRAM-based architecture that you talked about, you can only host models as long as it fits in their memory. As soon as it doesn't fit in their memory, you need to instantiate another node or a socket to sort of run that model. So it starts becoming very expensive, right? So because our model sort of allows you to have this extremely fast inference speed and switch between the different models instantaneously without having to boot up another AWS instance, you can run really good agentic systems on our platforms. And you'll see some of these demos today in the unique talk that we have, right? You can just run a lot of these agentic systems very efficiently on our stack, both from a raw performance point of view, but also from a cost point of view.
Yeah. There's actually a paper we wrote about it. It's going to appear in a conference soon, where we've tried to quantify this, saying, okay, what exactly is the cost that we need to pay attention to when it comes to agentic systems? And as an infrastructure provider, any workload kind of looks like an agentic system. Like I'm going to, because I'm not I can get away by saying these things because I'm not a hardcore machine learning person. But if we think about any agentic system, it's you have, like Urmish said, you have different models. You're going to produce tokens from one, which is going to feed into the input of the other, maybe with some post-processing in the middle. And this happens iteratively, and there's going to be a collective refinement, which is the output. So at some point, as an infrastructure provider, you need to host all these models somewhere, you need to put them somewhere. And then based on which models are participating in the agent, you have to do fast inference on them. So you need the models to be fast, and you also want the switching time to be kind of in the noise. And if you translate that over to, okay, how would you do this on GPUs, for example? You have to put all the models in HBM, right? Which means if you have more agents, or you have the sum total of all the models that you want to provide as an infrastructure person, if that exceeds HBM capacity, you need those many number of machines. So when we kind of compared it, a single RDU node, which is like 8 sockets, if you want, you can host models which are 19 times more than what you can host on DGX H100. So in other words, if you fill up one node of SambaNova entirely with parameters, the equivalent on DGX would be you need 19 DGX boxes to host the same in HBM. That's just a capacity play. We just have more capacity. That's the DRAM thing. The other way is, well, if you don't want to do that, like GPUs also have host, like a CPU, and CPUs have memory. And you'll say, well, I'm going to store it there, and I'll keep switching between the CPU memory and GPU memory. That switching happens on a very thin straw, which is the PCIe. That switching cost can be more than 10 to 15 times smaller. Longer, I should say, which means SambaNova switches around 15 times faster. So we have some results of the paper where it's like, well, if you don't pay attention to the switching, almost half your time is going to go in switching between the agents. Yeah. So at that point, that's not a good user experience. If you're able to switch between them because of this 3-tier thing, it's much more natural of an architecture. And we can kind of see this in Nvidia's trajectory as well. Like Grace Hopper, for example, like they have another layer of memory. Although they've not come out and explicitly said it's going to be agentic and so on. You can see that there is a requirement for another layer of memory. It's kind of being validated by other solutions like that.
I see. So I'm curious. It seems like you've done some experimenting with agents. Is there kind of like a sweet spot that you've found for maybe like the type of model that you find runs good with agents? So, like I think like in a certain sense we might think like, oh, like I just want to use the biggest model possible for my agents because this can be maybe the smartest. But then like maybe it'd be a little bit slower, and then if you get the slower model, but then it's not as smart, and then it's like way faster. I don't know if have you done any research into like what the sweet spot is there?
Yeah, it's a very open question. So we are still figuring that out. I think one of the interesting things that we notice is people would sometimes find a sweet spot, and then we realize they are finding that sweet spot on a system like GPU where they are more hampered with sort of what they have. They can't really run fast inference or switch between models. And then we sort of do things on our stack. It looks the trade-offs look completely different, right? So I think it's still a very open question. Part of the challenge is the models are also always changing. Like the models are getting really, really, really good. 1 year ago, an 8B model, if you look at it now, a 3.18B is almost as good or maybe better than what Llama 270B was, right? So all of these trade-offs are very, very sort of changing every day. So kind of hard to answer. I think some rules of thumb that I personally use is if I want to use LLM as a judge, use a larger model. So the smaller models, there's a lot of generation, and to pick and choose which generation was correct, use a larger model so that you incur the cost of a larger model only once, and the workhorse becomes a smaller model. And then you sort of use that kind of a system to build your agentic system. But again, as these models are improving, these trade-offs will keep on changing. And then that's where, again, sort of coming back to the platform. Because for us as a platform, we can switch between these models so easily depending on, and we don't care whether it's big or sort of small or large. And with size, we don't have to scale out, right? We can stay on the same system. It just becomes very easy for us to do all of these analysis, not just for us, but for our customers also as and when they come out.
So we talked a lot about performance, memory optimizations. I assume all this comes at some cost, some price to the end users. What is like the price difference, let's say, of generating like 1 million tokens for the latest Llama model, both in terms of like the explicit costs and maybe like the implicit to change some of their infrastructure to account for SambaNova Systems?
Yeah. I actually don't know what our price per token is. I just remember it was competitive. I don't remember exactly.
So the price per token that we charge is, there are other factors influencing that, which is, you have to be competitive in the market and so on. But I can speak to the infrastructure and what is the costs in some sense. And I can answer that in terms of 2 variables. One is performance per area, which is we have a rack. What are you doing with a one rack? And how many tokens how many racks do you need to run a model and so on. And the other one is the performance per watt, which is what is the power consumption. And I think for both scenarios, all the models that we have in the cloud deployment, they're all running on 16 sockets. 16 sockets is one rack. And a single rack is because of the details on, how big our chip is and where we end up, using power, it tends to be much more power efficient and hence more energy efficient than some of the other deployments. One is because it's a different technology node. The other is you end up using your on-chip sort of HBM. If you look at where the power goes, it's about half of it is in data movement in inference, or even maybe more than that. So the more you can capture, more data movement you can capture on-chip, the lesser the power. So that's one of the unique advantages of data flow. So, we haven't made it public, but, we have, actually we might have written a blog about this. We have a energy efficiency gain of, almost up to 5x compared to H100s in some benchmarks. I think there's a public blog post on this or LinkedIn post or something. That directly translates to cost because you're paying for the electricity. It's the operating expenses. And if you're able to squeeze out, more tokens for less power, that's being energy efficient. The other part is the performance per area, which is how many racks do you need to sustain these many number of users? That's where the capacity comes in. So 4 or 5, you said you liked it was very fast, still running on 16 sockets.
Yeah.
Right. So it's not as the models increase, as the model diversity increases, that doesn't put any pressure on, now I need these many more racks because I need these many parameters. Because those axes are decoupled, you can use your hardware much more efficiently. That also translates to costs. So in both those regards, even though two different parts of the system is helping, one of them memory, the other one is the data flow part, it tends to make it much more cost effective to become an inference provider.
That makes sense.
Yeah, I think we have a kind of a blog post somewhere that you can find on our website. And the number that I remember right now is 10x cheaper to sort of host models, just because of the sort of things that he talked about.
The other line of questions that I had was the competitive landscape. So there is a couple other companies that have come out that are touting like really fast inference. Before the SambaNova announcements, there was another King of the Hill, Grok, which was really fast. And then you guys came out and I think it was like twice as fast as Grok's inference, if I'm not mistaken. But I'm sure there's going to be more competitors coming out. Because
Remind me again, are they doing 405B?
No.
I don't think they've done the biggest model. No.
I think they did have early access. They had it up for like a day or something, then it was brought down. Okay. But I think...
So is that a competitive landscape?
It depends on the use case, I guess. Depends on the price point. They might have a cheaper price point at some of the smaller models. And then one of our friends also works at Cerebras, and they're thinking of IPOing, and they have a different solution to this. What do you think about this competitive landscape, and do you see like more architectures? You talked a little bit about SRAM, what you guys are doing, and the traditional GPUs. Do you see like other architectures, especially in your research at Stanford, and where the future of this space is going?
Oh, for sure. I think there's. Just because of the amount of interest, it's bound to attract a lot of smart people to think hard about. You always find something to innovate in if you go one level deeper. So this is one of those cases where, why wouldn't we do X? It could be different ways of stacking, different packaging methodologies, and so on. On the couple of other startups, I'm assuming you're referring to Grok and Cerebras here. They've done a good job. Like there's no, it's definitely an engineering accomplishment to scale to 500 sockets, building a wafer scale compute engine. They've done an excellent job. It doesn't change the fact that SRAM is not as dense as HBM. So there is this trade-off between capacity and bandwidth. So if on one end, if we're saying the models are going to get more, like the world will have more net parameters overall, we need larger context lengths. There are more people who want to use inference, just larger batch sizes. If everything is increasing, and you have a memory technology that's not going to scale with technology beyond a certain point, it's just physics, then you are eventually going to run into other kinds of limitations. That's one of the things I wanted to mention. Not to take away from the engineering accomplishments, right? I mean, I do want to say that it is, I'm sure they have more tricks up their sleeve, as do we. Yeah. So it's I would say we are kind of in this race together. But we of course feel like the way we have built it is the more scalable way of doing things.
And I think, and more players I think would enter. We had recent fundraising of these photonic startups coming up. As you said, the market is big and a lot of potential. So you'll see more smart people figuring out different solutions. I think one thing that needs to be sort of thought through is always, it's not just the hardware. The software ecosystem matters, right? And the software ecosystem takes time to mature, and you really need to focus on doing a lot of different things with your software and running a lot of different models so that your software ecosystem is always improving. I think that's what gives me confidence more in SambaNova, just the amount of number of models that we're running, both training and inference, the size of different models that we're running, that it just looks like we are at a better state in terms of software ecosystem than where other people are. So the hardware and the complementing software, they're both sort of going well right now.
The only exception to that statement I can think of is Nvidia.
So
the 800-pound gorilla in the room, with a 3.4 trillion market cap competitor in the room. I guess why did you both decide to join a smaller startup or start your own startup as opposed to joining this dominant player?
Well, my case is a little different in that I prior to coming here, I was a graduate student at Stanford, and there's a group of students, I was part of them, and we came up with this initial proof of concept of this data flow architecture. So the evolution for me was the journey, it took me from academia to industry, slightly different. So in that sense, I wasn't really looking for a job to go to Nvidia or anything. I didn't have to. But the other thing is it's the promise. So we know that Nvidia has done a great job. I mean, they've invested billions of dollars in not just building their software ecosystem, but teaching it. They've grabbed tons of mind share over the past decade and a half, where people understand what SIMT programming model is, what GPUs are. And I got into this field because of CUDA. That was my first internship, so to speak. So they've done an excellent job in grabbing the mind share. But we also understand that with the programming model comes limitations. So if you want to make a difference, an incremental change is not really the way to do it, was one of the sort of takeaways. You have to think about it from the ground up, from the grassroots level, which means it's a lot of work. You do take on a lot of risk, but the reward is, 7 years later, we're able to see that we can routinely outperform them in spite of having half the bandwidth. I should have mentioned that earlier. So all the one TGX box, one data scale box, which has 8 sockets each. We have half the bandwidth, but twice the performance, right? And it's not a magic thing. We just happen to use the memory more efficiently. So that was just the potential of doing something like that is the allure of a small startup was that. I don't know what would be your story, but that's me.
Yeah. It's a few reasons. So firstly, I've always been a hardware enthusiast. I come from a background of computer architecture. Before I switched to ML research, I was doing computer architecture at Wisconsin-Madison, working on data flow compilers, right? So I didn't spend a lot of time there, but spent enough time there to understand the potential impact that it can have in terms of performance. So I'll always cheer for new hardware startups that are trying to sort of change the ecosystem, right? So that's one reason. Second reason is, when I've been in ML for a long time, and I really, really enjoy personally these problems around hardware software co-design. How can you rethink algorithms to really suit your hardware performance? You really need to sort of deep dive into machine learning, understand a lot about why things work the way things work, and how you can restructure them and rethink the math to actually make them run faster. So that's a very interesting problem that I personally kind of enjoy, right? Coming from a hardware background, it becomes my problem to solve in a way, right? And I think third thing is I genuinely believe that from a purely ecosystem point of view, it's important to have multiple players. You cannot just have one dominant player because the ecosystem is never going to grow, right? If you really want to, or if you're really serious about democratizing machine learning, it's important that you democratize training and inference. And platforms is where it starts, right? So that also was one of the reasons I really wanted to sort of join a startup. Again, why SambaNova? I think reasons have been discussed before. As someone who comes from a background in hardware, I could see the appeal and what they're trying to do and sort of why they're going the way they are. And been here for 4 years, don't regret it. And I do think it was a good call.
Yeah, I mean, this is definitely an exciting place to work, especially having the fastest inference in the world right now. And both Mark and I think, understand what it's like to work at a big corporation. Yeah. There's a lot of comfort and stability, and we're building large products at scale, but with that comes some overhead of bureaucracy, and we can't move as fast. We have to think about scale and making everything compatible for everyone, all of our customers. So maybe Nvidia is in a similar place. I don't understand the hardware side as much, but maybe they have to move a little slower than startups can.
Yeah, possibly. Right. I mean, I also don't know what goes inside Nvidia and how they think, but in general, a larger company, the bigger the ecosystem that they already are in place, the harder it is for them to move quickly.
Speaking a little bit about the education side, so most of the research in like ML, I think in the last 10 years ago, was either at universities or Google. And then I think in the last 5 years or something, the industry just started sucking all the academics from the best universities, and they're just throwing money at ML people from top universities. So, like you said, you started or joined this journey about 4 years ago. What was the education landscape and the amount of research funding or the enthusiasm in academia like? And were a lot of other people also leaving academia for industry?
Well, for 7 years actually, not 4. Sorry, I agreed, but now it's 7. But there's no shortage of enthusiasm. I mean, I would say the machine learning class at Stanford, taught by Andrew Ng. I mean, that's the most widely taken class on the planet, probably.
That was on the undergrad side.
I mean, it's open to everyone. So you'll find people, undergrads, grads, not computer science majors, everyone. I mean, they I don't think they book the stadium for the class, but it's pretty. I think it's something close to that, where you have so many people, so many posters. That class has more TAs than a normal computer architecture class would have students. It's like 50, 60 or teaching assistants. There is no dearth for popularity and the set of people working on it. Right?
What about as you go farther along on the graduate level degrees or PhD candidates?
Even with that, so I think the one thing that even, I know we say AI and ML, we use it as a very broad term, but there are so many niches even here where you find specializations where people are trying to find across domains, what are the core design techniques that you can apply between two domains. I mean, it's something that we ourselves do here, saying how can we advance the field while we use what we have here. Our own co-founder, Chris Ray, has a lab at Stanford, and he does all sorts of things. How do you increase the context length from today? Llama has 128,000 tokens. I mean, there are fundamentally new architectures with state space models, which are like 1-2 million tokens. The existing approaches can't scale, but for that you need to go one level deeper again and invest in a much more radically different approach. Not all the ideas might pan out, but that's the seed. And the path from coming up with a cool idea in academia to being adopted in the industry is probably the shortest now, because you don't have to wait for a publication to be accepted in URIPS or ICML or something. There's a cool idea, you're able to explain and you're able to justify it. I guarantee you that someone's going to be watching and pick it up. Right? That's the bar is, in that way, it's the best time I would say to be in this field.
So I'm. Oh, go ahead.
And the ML, I mean, it's not just the top labs, right? You have a lot of startups in ML coming up. So the talent is kind of spreading out, and people are excited about it. They want to take on a new challenge. So I would say, yes, a lot of excitement. You see the number of PhD students increasing significantly in these domains. The amount of research that is coming out is just insane. It's impossible to follow research anymore. You go to these top ML conferences, it's like 10,000, 15,000 people. So you can just see the amount of enthusiasm throughout everywhere in the world around that, right? So yeah, I mean, it's a great time, and it has been this way for almost 6-7 years. I remember going to, I think, EMNLP, which is the top NLP conference, or at least was at that point in 2018. And they were just not ready for the inflow of all the people that were coming in. We actually ran out of food on the sort of the reception to them. And I was just 10 minutes late.
And there's this plot from Jeff Dean and David Patterson. I don't know, you probably have seen it. It's an old plot now, so it's even much more exaggerated now. There's one plot saying Moore's law, which is, it's an exponential. Like something is doubling every 2 years. Another plot saying the number of archive papers. Archive papers is going faster than Moore's law. Just that the sheer volume of people thinking about this it's staggering.
And the most beautiful thing about all of this is that a lot of this is happening at a grassroots level also. Yes, top industry labs, they have kind of stopped publishing, but a lot of interesting innovation is happening in the grassroots level. You have one of these I don't know if they're NGOs specifically or not, but Elither AI, ML Collective, all the other organizations doing a lot of these fundamental ML works with the compute that they have and pushing the boundaries and talking about it without actually publishing the paper, more releasing the artifacts, releasing blog posts and educating everybody. And those things are turning into well-adopted technology, right? The rotary embedding or the rope theta scaling that we talk about in the context of extension without training. That was kind of, I think, was a random Reddit post somewhere someone did. Someone found interesting. People loved it. A lot of thumbs up. People picked that up, improved upon it, and then it showed up in a Llama 2 or Llama 3 paper. I forgot which one. I might be mixing stories, but I mean, there are such stories that... and if you see this word of entire synthetic data generation, a lot of innovation is happening in the open source communities. People working at the grassroots level, in startups, in these decentralized labs. I don't know even what to call them, right? Like it's just people on Reddit, people on Twitter, just figuring out recipes. This Nose Research, Analysis, I don't know how to pronounce them right again, sort of open source kind of collaborations. It's amazing.
Yeah, so I'm curious. You mentioned about like Moore's law, and I feel like a lot of us, we speculate like for those who don't know, like Moore's law is roughly defined as like the number of transistors is going to double like every 2 years, but some people have kind of transitioned that to say like, oh, the amount of computing power will sort of double every 2 years or 1 year. What do you think? Do you think that like that trend will continue, or like I've heard Moore's law has been dead for like the last 10 years, but I'm not sure. What do you think?
So I actually have a great quote to answer your question, which I read recently on probably Reddit or LinkedIn. It said, the number of people who are predicting that Moore's law is dead is doubling every 2 years. It was fantastic. And I mean, I think, so if we look at what Moore's law is, it's, yeah, like you said, it's your computing power, overall capabilities is increasing with, it used to be every year, then became every 18 months. Now it's every 2 to 3 years. But it's some exponential, which is kind of slowing down. And earlier, there used to be two effects. One is because your device or the transistor size is decreasing. You also could lower the operating voltage. So because of that, up to a certain point, as you shrunk the size of your transistor, you could pack more transistors onto the same area, double the number of transistors, at the same power. So that is a straight up increase in capability without having to increase the power draw. That scaling stopped. It's called Dennard scaling, and that stopped for now. It's you don't see the same scaling anymore. We do see shrinkage in transistors, but so for example, there are our first chip was a 7 nanometer part. Now it's a 5 nanometer part, and there'll be 3 and stuff beyond in terms of technology scaling, and the physical designs have. There's a lot of innovation there. What is also true is that transistors is only one component of a chip, just that's the thing that makes up the arithmetic logic units and, the muxes that are and all of that stuff. And the SRAM, although the SRAM bit cells are constructed in a different way. So the SRAM, the memory cells and the compute cells, the transistors, they scale differently. So beyond a certain point, the memory cells don't shrink anymore, because of other reasons. But more importantly, the communication between them, the wires, where you have like an interconnect on chip, there's a crossbar here, and those wires are implemented using metal layers on top of your silicon, and that is not scaling at the same rate. So which means even though you have a lot of transistors, you might not be able to power them beyond a certain point. And the way you manage your interconnect, that becomes a lot more important. But there will be scaling. I think there is, I wouldn't call Moore's law as dead, because otherwise, we wouldn't be looking at, okay, what's the newer thing to be done? But I would say that it's not the sole knob for hardware improvement. We do see much more advanced packaging technologies now, like chiplet designs, where, you do what you can on a single chip, and then you play a packaging exercise where you connect them, multiple chips together in a certain multi-chip module, or like a chip on wafer on a substrate, like CoWoS style 2.5D packaging. All of it is effectively saying, I'm going to give you net more silicon area, but it's accomplished using these other techniques. So I wouldn't call it dead. So long answer, short summary, no, it's not dead.
Okay.
But you can't rely only on that.
That's good to know. And that's also exciting, because I'm all here for the exponential growth. So I know we are kind of running out of time just because we have an event that's going to start soon. But I am curious. It seems like it's incredible that you were able to have your PhD and turn it into a company. Do you have any advice? Let's say you're somebody who's maybe a graduate student, maybe an undergrad, you just have an idea. Is there any advice that you'd give to somebody who is maybe in like a similar place that thinks like, hey, like I have an idea, I want to start a company, like any advice you'd give to that person?
Interesting question. So first of all, I want to say that it's because it's a systems project, it has it has always been a team effort. So even at Stanford, it was a group of graduate students who sort of collectively brainstormed, argued, iterated over, and, we came up with what we came up with. And even within the company, when we decided to start and transition, it's the group, it's the collective decision. So I would say it's equal parts technology and people really that made it happen. And I happened to be at the right place at the right time. So it was very fortunate. It definitely helped that we were prepared with the right amount. We built sort of the real thing when this transition opportunity came by. So just based on my own experience, one is you can never time any of these things to perfection. But if there's an idea, chase it and build it, and good things might happen. And talk about it. Like if you do some cool things in a vacuum, it's very hard to, especially now with so much happening, it's very hard to discover. And nothing speaks better than something that works.
Yeah.
So I would say one of the things that, our co-founder Kunle, who was my PhD advisor back at Stanford, a bunch of fortunate things happened, but we were able to act upon it because we had enough ready saying, okay, this could be a good starting point. And then a whole bunch of things happened within the company. But if we weren't ready for it, then, something else would have happened. So luck was there, but I think just go chase down if you have a cool idea, and find the right angels who can advise you and guide you in the right way. I think that's... Don't sit on your tree, is I guess what I would say.
Yeah, I think that's really good advice. Also, I thought it was really interesting how you mentioned that it's good to kind of share the idea too, because I see a lot of people, they kind of are very secretive about their idea. They kind of have this belief that's like, oh, well, I'm just going to build kind of in silence, and then like I'm going to do this like big grand reveal to the world, and then nobody actually cares what they do. And I mean, like, maybe I'm sure there are exceptions to that. Like, I mean, if you're the type of person who's working on like cold fusion and like your time machine, it's like maybe then you can make it in secret. But I feel like, most of the time we're not doing something of that kind of extent. So yeah, I like that. And also like the people. So I'm curious, how did you find your co-founders?
Yeah. So I think just one term. I'm not a co-founder of the company.
Okay.
I'm one of the founding sort of employees. So we have 3 founders: Rodrigo, Kunle, and Chris Ray. And for me, it was, since I was a student at Stanford, I knew Kunle, of course, was my PhD advisor, and Chris Ray is, we had a shared collaboration for a long time. So although Chris wasn't my advisor, we spoke almost, pretty regularly. I don't know the cadence, but we spoke pretty regularly. And Kunle and Rodrigo have a shared history before. So Kunle is, of course, he's known for his prior work on sort of multi-core processors and domain-specific languages and all these things. And his first startup, which was called Afara, tried to commercialize the first multi-core processor. That's where Kunle and Rodrigo, I think, their first interaction happened. So ever since that connection, and Rodrigo, of course, then led the whole Spark division, our CEO, from Oracle. So that shared connection helped us, translate what we had come up with at Stanford with the right sort of industry experts, where they're able to spot the stuff that had value and then improve the stuff that didn't have value.
That's super interesting. Yeah, so that's all the questions I had, but I am curious, is there anything that we didn't ask you that you feel like needs to be mentioned? Anything you want to plug? Anything you want to ask us? Kind of the floor is yours.
Only one plug. Go to cloud.sambanova.ai. Sign up for an API key and try everything for free. Whatever we've talked about, it's all there.
And show us what you built. We would love to see.
Yes.
We'd love to see what you've built. Tag us on LinkedIn. Tag us on Twitter.
Yeah.
We'd love to see what you've built on top of the APIs.
Yeah, for sure. I mean, we are also, our intention is also to be more open. We want to learn. It's the same ideas again. Like the community is out there, so there's no reason for us to guess. So anything where people use, even if you don't tell us anything, it's already a lot of valuable information for us.
Yeah, that sounds exciting. I want to use it for the next hackathon and see what I can build specifically for agents.
Awesome.
Yeah, of course.
Glad to hear that.
Yeah, for sure. Like, I'm definitely going to use it just because, like, the price, we were looking at, it seems very competitive.
Yeah.
And also, like, the speed, I feel like
So fast.
It'll be good for, like, a hackathon because the thing is that sometimes, like, you need to, it takes a while to get, like, your response. So it'll be nice. So I'm ready to try it out and use it. I played around with the cloud. I'm impressed, but yeah, I'm ready to use it more. So yeah, awesome. Well, thank you so much for like your time. It's been like an awesome conversation. And yeah, so thank you everybody. We'll catch you in the next one.
Thank you.